system. So I'm Carlo Cipolloni. I'm technically responsible for the environment information system in Italy. And I'm coming from ISPRA. The acronym is similar to the place where is the GRC, but it's two different things. ISPRA is the Italian National Environmental Protection Research Institute, so it's quite funny things. And since 2016, a national law defined the national environment protection system that composed by the national one organization represented by ISPRA, plus all the regional agency of environmental protection. So the law decided that fix a very clear situation where it's a national information system coordinated by us with the region. So what we're presenting today is how we set up strategically and operatively some approach to be a system, a compliant system, also to provide reporting in SPI format. You understand now that if you have a system, you have a complex system, because you really, not all the environmental reporting and environmental monitoring take place in the regional agency. Sometimes take place in the region. So the data is in the region, not in agency. So we have a complex situation where we have the regional environment information system called SINA, no? That in sometimes is all included inside, but sometimes is interlinked with the regional agency. So the complexity is quite wider. In this situation, we have to have a pragmatic approach. From the one side, we're starting to have a vision how to transform the data in something that is quite useful also for the citizens, for the people. So we have a SINA data chain that defines that when we have the data in our repository or in the regional repository, we must transform this data in a harmonized way, looking to the inspired data model, eventually with extension. Another thing that is quite important that I want to highlight is that one, that we decide to set up at the national level a registry for persistent identifier. And so we want to use the persistent identifier to interlinking the regional data set with the national one. So we not to replicate data if not needed to use this data in a single point. And this approach permits to us to have some repository where we deployed inspired service or inspired load. Yesterday morning I presenting marine network services, marine monitoring services provide in Inspire linked data. From this side, we pass to the other side, the reporting side, that is something that we have to oblige to follow. So we design also a general workflow to take in account the regional system and the national one to produce the reporting. And we have the regional repository that in some time go directly in a national repository, or we manage in different way with the persistent identifier. All the data set and the service must be metadata compliant in national catalogs. The national catalogs is federated by us, and we have also the opportunity to have the metadata available in our system. This allowed to us to produce also metadata for reporting that we provide, of course, for a UNET system, and to be linked inside the European Inspire portal. If you look into detail this workflow, we see that really we have some elements that recurs. We have the regional repository. Some region, we try to enforce the region to make some harmonization looking to the SPIRE. They produce, of course, metadata for service and dataset in the national catalog. And then we archive this one in a national data repository, the ISPRA SNPA. SNPA is the National Protection System, to provide in compliance schema with the SPIRE services in different format, of course, and metadating in our catalog that is federated in the national one. So this is more or less the general workflow that we design. I don't know, we have two. Okay. Just the light here that in all the case we have the persistent identifier. This is quite useful to have a clear identification of each data set coming. And also if we have a national one, we have the reference with the region, because we have inside the national one the reference for regional provider. To set up that, we have designed a new strategy for spatial data infrastructure. So we have implementing some activity and tools to harmonize data and integrate data at the database level. We provide, of course, we have the catalog layer that is able to do that. But I have not spent much to explain the metadata catalog. But what we set up is a strategy to provide REST service, view service, atom fit, download service in different format, using different approach and software. Also, to optimize the result. The database is the same, so we're not changing the database. It's one unique database. But we provide service in different systems to be sure that we have high performances. Also because at national level, we have to provide quickly response for environmental risk. And this one, of course, are also integrated in the view visualization layer with the client, with the platform. Then I spend a little bit more about what we set up, especially for the citizen consumption of data. But internally, we have also designed a data management system. So we design, we have already data acquisition system, but what we design especially, and we spend a bit time in the next part of the presentation, we set up a data integration to produce some data layer. Of course, we have also the other elements that we need to manage the metadata and data in terms of visualization and search engine for discovery service. And if looking in detail the data integration, what we have done is develop specifically dashboard with elastic search engine that is quite important, powerful elements to look into the data, to integrate the data, also with the different sources, not only in the local database, but also in the service. If the region provided the FFS or other feature service, we can integrate in the system to produce different products. We using this one for make analysis to produce a national report. On an example is the urban environmental quality annual report or environmental status report and so on. Or we're using the integration data to produce indicators. So we're using the data coming from the region to produce some environmental impact of environmental status indicators to have a trends. So to monitoring the quality of the environment. And we're using also the dashboard to make some data integration analysis to produce, of course, the reporting for European legislation. I show you now a couple of examples that we using to archive the data with the regional system. The first one is related to the air quality. The air quality system, we have the region that need to provide the different data set of air quality, also the real-time data, up-to-date data sets. So we set up a system, internal platform that is able to receive a different format from the region, and of course at this level make the first validation system taking account the IQD schema, and also a system that archives in a repository timely schedules all the hourly up-to-date air quality information. All the information go to the national database. In this database, we have the INSPIRE harmonization, the air quality IQD harmonization, and with the internal dashboard, we produce some indicator that's useful also for the citizens. So these indicators are automatically in a real time linked in the web page, so the people can see exactly which is the status of environment of air quality in some place. Or we set up a special dashboard, this one, to produce directly the GML file for commission. So automatically we have all the data set available to put in the repository for the commission. This is one example. Another example that is not totally related to environmental reporting, but more environmental monitoring in terms of electromagnetic wave impact, is this one. We want to have a database that is in line with the regional one, because the region is the authority competent to make some changes on this database, also every day. And we testing this system based on the Restify DB. So the region have the same system, Restify. We're using the post and get property of a database to make some changes in the database. And then we're using directly in the central one the put command to receive automatically the package of changes. So the national one remain aligned time by time with the regional one. And we have the national one available for some analysis and data production at the national one. So this is another system that we have set up to produce indicators and products on the environmental status. This is two approaches that we're using to archive data and to collect data for monitoring and reporting. But in the other side, we have to take in account the opportunity to integrate the collaboration of the region to produce also data for citizens, for people that want to know exactly which is the status of the environment in the country. So we have set up a system based on the commercial side. We have our system is based on the server, ArcGIS Server Federation, with the GIS portal that is available for collaboration. What we set up now, we're working in this week to finish the system, is a federation with the regional server. So in some way, we have all the region that have some server available for data interlinked in our system. And the system allowed us to have a collaboration platform where you can also using the data dynamically, also in the risk event, to make some changes on the data in collaboration way. You have groups, you have specific domain groups where you combining that. But also when you have a very concrete layer, or you have to finalizing your data in a visualization event, you can produce a storytelling or web app that's integrated in the portal. This is our national system Environmental Protection GIS portal, where we have the collaboration with the region. So in this portal, you can find not only the ISPRA application, but also the regional one. So in some way, the people can find in the same place the possibility to explore all the applications that show exactly which is the status of the environment. This is more or less the name. At the moment, it's the internal domain. Will be available in a few weeks because we make some security tests, for sure. But we are ready before the end of the year because we have an official launch in December. Some conclusion or some next step that we want to remark. So the new system, the new cloud system, now we start to be populated by ISPRA in the region. And really, ISPRA already prepared some maps, some application that is available at our website. And also some regions have the same things, but now we have to integrate this application together. One very specific task that we perform in the next months will be some specific application for citizen science, especially in biodiversity. We're using to define and develop an application for the bear rings system that we're using at the national level for take information for that, but also something regarding the adaptation climate change activity that we have in charge to develop. And the last sentence is related to the fact that we have also to, I show you a couple of examples, but this example I have to reply in all the 18 different data flow that we have to manage in our system. And the idea is to have this in place for the middle of 2019. That's it. Thank you.
Good morning, everybody. I am Andrea Vianello from Eurac Research Center that is in northern Italy, and I'm here to share with you our experience with our environmental data platform. Before I want to introduce to you our institute, that is an institute for Earth observation, and so the main goal is to monitor and understand the key environmental dynamics in mountain regions and related climate and disaster risk. So our institute collects many data sets deriving from Earth observation system, so remote sensing, in situ sensing, and also proximal sensing. And the main three research line is the water cycle, the ecosystem dynamics, and the natural hazard. And so you can understand how important for us are the web services to share and to process the data set. My group is the group for the technology for environmental monitoring, and we have two research lines. One is for the sensing technologies, when we manage the hardware, so the sensor, the real stations. Then we manage also the software in order to help the researcher to use this sensor and to organize the data set that the sensor products. Then the other research line is the data management and processing, where we help always the researcher that are not really good, they don't have a good technical skill normally. We help for the ingestion, for the organization of data file in databases, or also in file system, but for sure in web services. And then we provide them the tools for the analysis and to obtain new products. So we set up an environmental data platform that is composed by open source software, so web application, like first of all our catalog. We use a GeoNetwork at the moment, and the catalog is a standard CSW service, and this permits us also to connect to the GEOS portal. If you know, GEO is the group for the Earth observation, so it's a community of researchers that need to make a network So also this may be a good example of how working together. Then we have map services like Rasteman that you know for sure because downstairs there is the presentation, and also GeoServer that is, or I can say, very common, so I don't want to lose time here. Then we have a sensor observation service. We use the 52 Nord implementation that is working pretty good, and we are really happy. And we have several databases according to the needs of the project of our researchers. All of these applications, or most of them, have its API to access the dataset. And so through the API, all the clients can connect, query, process, download the dataset. The clients may be different, like desktop application, like QuantumGIS, GRASS, whatever you want. Then we have many web applications that we developed in order to help researchers for specific needs. And then finally, but for us is really important, is the possibility to access the application using some code, like the Python code or the R code for the processing of the dataset. And the dataset, as you can see, may be raster, vector, or table datasets. In the last year, we worked a lot on the sensor observation service because it's working very well, but it's not easy for the researcher. So the uploading of dataset is not very user-friendly. So we worked a lot to improve the usability of the standards, so the standard of the sensor web enablement. Specifically, we are working now in the LTSER project that collects dataset in a valley of the north of Italy, in a small valley in our province. And here we are connected to the LTR Italy network that is a research community for ecological dataset. Overall, there is also the LTR Europe community, and so I think this can be a really good example of network and interoperability needings. So the research problem was how to handle multiple data belonging to different sensor, different scale, different output format. And our needings, and so problem was also how to automatize data into the database in a near real-time system. And for sure, we need, first of all, a standardization of the data file in order to get a real interoperable system and to share our dataset through all the community. Our solution was to use the implementation of the 52 Nord, so the sensor observation service, that for sure permit us to follow the sensor web enablement standard of the OGC. And plus, we developed our system for an automation system using Python code to upload the dataset from more or less 500 sensors that continuously register records of observation and need to send in every 15 minutes, let's say, the data to the service. So the workflow starts in the field campaign, where we collect many datasets, and the station sends to our cloud system all the dataset. And here our group starts the work because we need a pre-processing of the dataset, so a quality check if the sensor is working well, and the standardization of the data output. So after this, we have to organize the data file, so the input for the database, into a specific folder that we organized in order to offer a clear environment to the research. So there is a folder for the data input, a folder for the data configuration file, a folder for the Python script, and I can say it's very easy to use. And finally, we are ready to run our script and to upload the dataset into the sensor service. So what really the researcher has to do if he wanted to register a new sensor to the service, is just two things: the creation of a configuration file for each sensor, and then to standardize the output of the station of the sensor. After this, the researcher doesn't need to think to something else, because there is an XSLT code that transforms the configuration file and obtain an insert sensor to register to the service. And the same XSLT code produces the insert observation template. And finally, our script can read the template, the input data, and upload the dataset to the service every 15 minutes, because it's just the time that we decided together with the researcher. And so as a result, we produced the LTR database for our project that collected time records since 10 years. So there are more or less 80 million records. And we are happy to develop this automation system that is working very well and that we want to share with the research community for the LTR project, but that we can share with everybody needs. Then finally, we have our LTR sensor observation service that if you're interested, you can have a look, that collects dataset every 15 minutes and is working. Also this morning is working, so you can see an example. And we have our viewer, the Helgoland viewer, provided with the 52 North. That is really nice to have a preview. And finally, we developed also a plugin for R in order to make the work of the researcher more easy, to access the data set in the API of the sensor observation system service. And here there is just a quick look of the Helgoland client, where there are the public observable properties that you can query. And it's nice client because you can add external provider. So I think this can be a good example of networking. And for sure, it's useful for the LTR community. So we are really happy about this. As future work, we need to improve our environmental data platform. And we need to insert in the middle another level that is a common API. This API is developed in the OpenEO project that has the main goal to develop this one unique API for authentication, authorization, access, discovery, visualization, and processing. So this helps the researcher and all the clients that need to query our web services to access one unique API. So it's more easy. You have to use a unique language, let's say, and you can get the authentication for all the services that our institute provides. If you're interested, take a look to this project, because I think it's very useful for all the research community in particular, but maybe for everybody. And so if you're interested, just take a look. From my side, it's all, so thank you very much.
I actually work in the ALTA project, so I was just, sorry for hijacking, I was just curious whether or not you were already providing the data to the ALTA data integration portal.
Well, we are working with the LTR community, Italy. So now the system was ready since a few months. We are still testing, and we are in this phase. So later we will be provide the data set to the network, really. So now we are at the end of the test phase, but it's ready to be used, let's say. Okay.
Good morning. I'm here to share with you our recent experience related to Inspire Data Harmonization and its relation with the ongoing issues that we are involved in, namely some of the most relevant research projects that we are involved. I come from DGT. DGT is an official data provider, has the cadastral attributions, INSPIRE implementation attributions, as well as land use planning and e-government data register. So these are quite relevant, these issues are quite relevant for us. In order to organize our ideas, I will give some clues on the main problem that the information we produce has to address, that is to respond to e-government environmental issues, and namely the framework, the environmental framework directives, and obviously give that information also to the Commission. Then some clues on what is going on in terms of INSPIRE data harmonization in order to build true knowledge, because e-governance and governance information quality is quite an issue. So then I'll share some of the examples that I brought to share with you. The main examples are related to water quality and nitrate intake, and then share with you some of our inside view in terms of conclusions. So the problem that you are obviously, I think, aware is how to improve the monitoring framework directives and their implementation among EU member states in order to achieve cohesion and development among all member states and being fair. The Commission being fair inside each member state, being fair in terms of the way we do things in the democratic institutions in European member states. This is quite an issue nowadays. So it's difficult to monitor environmental quality. It's necessary to establish valid assumptions among different areas or states that are facing and have different problems and have obviously different realities to deal with. To monitor the process and the requirements are more and more efficiency demanding. How to ensure efficiency and reliability within all these processes. How to be progressively more efficient and ensure that more and more can be done when the same or even less funding. How to improve cost-benefit evaluation and their redistribution among regions. And let's look to the INSPIRE data harmonization and have a clue on what does this means, at least in what we are bearing in mind when I'm sharing these ideas with you. Data harmonization is about data discovery, about data integration, about evaluating data quality and obviously fitness for purpose, because data can have good quality but don't fit our purpose because they have too large scales, or the issue or the purpose they were collected for is not the same purpose that we are using the data for, whatever. So normalized data based on comparisons among member states is essential to have this data normalized in order to be able to make good and reliable comparisons, to improve data accuracy constantly and align production with user requirements, and to align official data production and financial with government needs. In the present case that I brought to share with you, we have to report and help reporting environmental directives within quite different areas. The Water Framework Directive, and namely the nitrates evolution among not only water, but water, soil, air. And so obviously a link between these directives and the environmental impact assessment related issues. When we started a few months ago to deal with the INSPIRE data harmonization issues from the Portuguese perspective and trying to be in line with what are the INSPIRE standardization and specification requirements. And I just, not to be too bored, I brought to share with you a piece of work related to hydrography and the objects that we have to catalog and to define at this stage, and then to organize in order to be able to manage all this information properly. So we have two different kinds of objects, the natural ones here and the artificial ones related to the hydrography issue. This is a detail within the natural objects issue, and this is a detail related to the artificial ones. We are bringing to share with you, well, this is the whole scheme in terms of definitions and objects relations description. We then only look that we are only looking at one issue, hydrography. And obviously this relates to many others within the INSPIRE specifications and teams from the Annex 1, 2, and 3. So in dark blue, we have the objects that we had to properly describe and align in terms of INSPIRE specifications. This slide shows you the dam of Castelo de Bo. That is one of the most relevant waterfronts in Portugal, because here, well, near here, we have the pumping station that supplies about 1/4 of the Portuguese population with drinking water. So this is quite an issue for us to assure that we have proper data to assure drinking water supply for the Portuguese population. So it's all about knowledge building, data integration by location. It cannot be left on hazard. It has to be properly addressed. And we have to be sure that we are collecting the right data and that we are integrated it properly and combine it properly. So the data harmonization has to be aligned with the search engine's capabilities based on location. It'll enable member states to adjust the water quality monitoring networks to their local concerns, preventing impacts on natural resources, preventing water stress induced by quality degradation in this case. But now I hope that you bear in mind that it's not equal to prevent water degradation all over our country. And I think that in your country will be the same. But look at the Water Framework Directive. What it says is that we have to recover all waterfronts. And that means investment and money. So it's essential to understand, even so, the priorities, because we always in life have to establish priorities. So also, it will enable member states and the EU Commission to build their own inside view and purpose and propose new and more effective approaches to not only the framework directives, but also reporting capabilities and improve the contribution from member states' focus on effective resources protection and obviously in the way money is spent to achieve balanced development. So let's check some of the ongoing process related to these issues. The environmental monitoring potential improvements through data harmonization. So the examples I brought to share with you related to with water, this is some of what you can, data that you can have access within the environmental, the European Environmental Agency. And this obviously is what is the data available among member states that are provided when you check this on the web. But when you go deeper into a member state and you look, for instance, the case that I brought to share with you, that is where our research is about, you can see this is the Tagus River. So here is Spain, okay? And the Tagus River is shared with Spain. But we have within our reality this watershed that is mainly in Portuguese territory and supplies about 1/4 of the Portuguese population. So as you can see, the reality is changing from perspective when you go deeper into the problem. And so here on my right side, we have the different municipalities. And this waterfront, here we have the pumping station, and all this area is shared among different municipalities. Obvious, all of them want to develop their areas because that is what will give them votes and will enable them to stay as mayor of the municipalities that they have to organize and develop. So we can check what is the monitoring network within this watershed. Well, and what we are doing is evaluating if the network is good enough by crossing data, harmonized data, with all other thematic issues. Here, you check the evolution of water, and we are sometimes facing problems, and we don't want this to increase. So we really have to define properly the network. You can obviously look at this and see that probably we should have a much dense network within areas where we have drinking water issues. And this is the same that you can think when you compare data from Portugal with other member states, how to normalize this data in order to put into place reliable conclusions. This is what it is about. You have to rely on good data in order to produce those conclusions. So this is another project that we are now putting the INSPIRE specifications into place and try to see what are the improvements. And these are on the right side. You see in red all the urban areas and all the land use that you can use as another thematic issue in order to evaluate the impact on water and to evaluate in which extent harmonized data can do a better job. And this is the forest fires, because obviously we can also think about risks and addressing the problem of forest fires. This is the 2017, you probably heard about it. Portugal faced terrible forest fires. These were the burned areas. And obviously, if we combine different data sets, well, both harmonized but collected with different purposes, if we have well-structured data, we can be able to evaluate which each one better address our purpose, or if both address our purpose, if they confirm or if they point out to different water impact, I would say, evaluation, or different land use burnt areas. I'll go further on that in the next slide. This is just to show you that it's also possible to link all the land use with the Water Framework Directive in terms of this is our main issue within the Nitro Portugal project, that is to evaluate the the nitrates by each sector of activity. So related not only the land use, but also the statistics that are produced by each sector, and try to evaluate this contribution. And this is obviously related with this slide. that is evaluating with different data sets the same issue, okay? And see when we have all the same definitions and then when we are certain that we are really comparing things that can be compared, each data set gives us different perspectives. These are the municipalities. Red, you have the burned area of, for instance, here you have forest, you have the burned area of forest. You look, all the most relevant area that was burned was the forest area, okay? But the most significant differences between one and another that data set are related to the artificial area. That is because, obviously, the scale is quite relevant in order to evaluate artificial areas that were burned. But those are the areas that brought the biggest damages and that really require most large funding for the municipalities to help people that suffer from the forest fires. So we now can check why is it relevant for us, obviously, to count on people data intake, but we also have to be aware that when we are talking about governance, and that is a much more serious issue. So we really have to know what is the quality of our data, if the data are really well described, and if we are speaking about the same objects and the same things in terms of definitions, and so that we are really able to make good comparisons. So some of general conclusions, but we could discuss this whole morning, because we really are lucky to address this issue within several different projects, not only Nitro Portugal, that is about nitrogen intake, but also Forland, that is related to land use and land use cover risks evaluation. And we are working with the two relevant universities in Portugal related to all the agricultural and forestry issues, and also land use planning, to share all the experience that has been developed related to these issues. So monitoring and reporting is really the support, not only to define strategies, to define funding, to establish priorities like those related to water quality monitoring and understanding what this means when related to water quality needs. And the first need and the most exigent is water quality to drink. That is the main problem. Then the others obviously are also relevant, but come afterwards. And in the years to come, and not only related to the member states, but obviously related to the EU policies integration in order to address sustainable development concerns, the INSPIRE contribution within this context, namely INSPIRE Data Harmonization, can be a good opportunity to increase the way we do things and to increase the quality of our work, definitely. It is also the opportunity to increase trust, and increasing trust in financial resources allocation and doing much more with and much better, even if the budget still is the same. Because I think that when the money is not ours, we have to be much more careful in the way we spend it, because it really represents the work of others that put the money into our hands to manage it properly. Demonstrating the relevance, we will be lucky enough to have an increase in budget because our work is really recognized as relevant. And so we will obviously do even more relevant work in accomplishing sustainability and cohesion not only among EU, but obviously worldwide, and helping others that we can help with our knowledge, and obviously working together with them and receiving inputs also from them. Lots of work to do. Let's work together in order to assure that by increasing data harmonization, integration, and analysis capabilities, we are increasing and understanding available, reliable data, true knowledge for e-governments in order to address each country problems properly and try really to achieve sustainability development worldwide. Thank you. Thank you very much for your attention.
Thank you.
Okay, it's lovely to see that this is such a large crowd. So I'll be speaking about a project, a research and development project called SenSituMon, which aims to look at open water bodies in near real time, in essence, flooding events, if you will. This is a project which is a collaboration of 3 companies, Conterra, where I'm from, 52 Degrees North, and EFTAS, and all of them are located in Münster, Germany. It is a research and development project because we want to look at new architectural patterns, how to cope with large amounts of data, and we do this in the use case of the flooding events or monitoring large open water bodies. And before we started the project, basically, we looked at the landscape in North Rhine-Westphalia, which is the federal state where we are from Germany. And we asked all the geo people there, basically, today the potential of Copernicus is not sufficiently exploited in practice. What are the reasons? Because we were curious why Copernicus data is out there and why it's not really used today in practice in the geo-IT or geoinformatics world on a large scale. And the questions we got back were basically, there's a lack of knowledge, basically a lack of best practice information, then complexity and cost, because the large amounts of data which are created in the Copernicus context don't fit really well into our standard spatial data infrastructures, which we have established over the past decade or so. So there's a lack of ready-to-use information products, which you can just use, deploy, and say, well, this consumes Copernicus data and integrates it somehow with all the other data which we have in our spatial data infrastructures. And then there's the issue of market structure, that the geo-IT community or industry is, in essence, a niche. It's tough to hear that when I'm speaking in front of this crowd, but in the end, mainstream IT is different in the ways how software is developed and how software is deployed and how fast it moves, basically. So Copernicus is a can-do and not really a must-do, and due to a lack of coordination and cooperation and a lack of the market structure, it's not really used today. And those are basically the 3 reasons we identified at the start of the project, and we wanted to tackle those. Therefore, we have acquired additional partners, which are stakeholders in the essence in the project, which come from an agricultural sector, so land machines for, I don't know, plowing fields, then a partner from monitoring water bodies, and insurance companies, which are also quite interested in open water bodies, because when a flooding event happens, they need to know when and where that flooding event happened, and they need to know it fast in order to calculate how much money they have to basically hand out to the insured people. So this is the start of the project. And then we set out to formulate objectives for this research and development project. We wanted to create a fully automated large-scale monitoring system for open surface water in near real time, meaning that if I have a new data set coming up from Copernicus and a new data set which is distributed from a spatial data infrastructure, e.g. sensor data from a sensor observation service, we wanted to consume it in real time, process the data, and then within a day have the result of there is an open water body which has grown, basically. So that might be a flooding event there. So we need to know the actual extent of the water bodies, and we set out to test this in the federal state of North Rhine-Westphalia, which is a pretty large footprint in space, but not the entirety of Germany or even the European Union. But we have the aim, basically, to cover those in later stages of the project. So we start small, but the infrastructure or the paradigm we developed should be able to scale up for the entirety of the Federal Republic of Germany and Europe. And the data we use stems from various really sources, from open data sources, from Inspire sources, and from Copernicus itself. So we have water gauges, which are published as Sensor Observation Service. We have weather radar data, which is published as a WMS. We have land use data. We have several other Inspire and OGC compliance services flow around. We have some strange open data archives, which are published as zip files, which need to be pre-processed. And in the end, they all need to come together. And we, as I said, consider all the requirements of our stakeholders from the insurance industry, from disaster management, agriculture, and water management. So if you look at those objectives, certain challenges arise in the project which you need to tackle. So the questions for the challenges were which quality can be achieved in a fully automated process, because usually remote sensing is a semi-manual process where you really need to fine-tune the classification process. Then the question how to scale up from a federal state up to the entirety of the world potentially. How to cope with volume, variety, and velocity of the data in near real time, because in the end it's a big data project. How to integrate all the different sources, and how to make, and this is the most important point, use of the existing Copernicus DIAS nodes, which are spawning all around Europe. We have, I think, 5 now for the moment, if you count every one, and they always state if you want to use Copernicus data, you need to be near the data, so in a cloud infrastructure. And how does this cloud infrastructure, this DIAS node, fit together with a spatial data infrastructure which is hosted in your own data center? How to do that, basically. Those were the challenges. And after the talk, I hope that you will see that we've tackled all of them, or are in the process of tackling them. Methodological approach. So we calculate the flood mass using Copernicus data, especially based on SenSituMon data, because it's radar data. And radar data looks through clouds, and then you can see the water body and calculate an extent. We used digital terrain or elevation models and land cover data, and in the end it's a simple thresholding algorithm which looks at the Copernicus data, the SenSituMon data, and says, well, due to the backscatter intensity, the classifier, which can be a support vector machine or a random forest classificator, gives back the extent of the water body. Then we use in situ data, which stems from the open data community and Inspire OGC services. For example, we use the high water events, which are communicated from the rivers, from the Sensor Observation Service. We use data from the German Weather Forecasting Agency, which is Radoline data, and we use other water data, for example, other hydrological data from environmental agency within the federal state of North Rhine-Westphalia, the Hygan data. And you actually are sitting here. And all this in situ data is then used also to visualize everything in the end on a map, to have some kind of visual exploration in order to look at if it fits in the end. So if you have all this, you need a shift in perspective how you tackle the data and how fast you do. And the fundamental technical concepts are we have to be cost efficient because it's large amounts of data. We can't afford to have an infrastructure which just sits there and consumes money all day long if there's nothing to process, because flooding events don't occur every day. They only occur at a certain point in time. And then we need a large infrastructure really quickly, and then it needs to be shut down after all the data is processed. So it needs to be scalable and elastic. Then we need to have a stream processing paradigm. Let's keep the data moving. It can sit in a batch processing setup where you just process one file and the next file and the next file. So stream-based means that you are integrating everything reactive. As soon as something's there, you process it. Then it needs to be loosely coupled because every component needs to be able to adapt to new data which comes in. And you need standardized access to data in the end. And the picture there basically gives an idea. You have the red circles and the green triangles, which are events. And an event is new data, basically. Then it's sent through a message broker, in our case, Apache Kafka. And then it's processed, in our case, with Apache Spark, filtered and all this fancy stuff. And then the result is published through a standard interface. The system architecture is here. I'm not going through everything there, but if you're interested later on how it works, you can have a look at it. In the end, there's different data sources, Central 1 and 2, to your left, and the different other Inspire-based services which are there. And they are all somehow connected through a connection layer, which is, in the end, a couple of Python scripts which do that. They are published through the messaging cluster, Apache Kafka, processed, and then disseminated using standard services which are OGC compliant. The idea is that you publish and subscribe to a certain event. So if there's new data incoming, you don't wait for it, but you receive an event, a message basically saying, hi, here's new data. You can think of it like an instant messaging tool from a point of view, like if you use WhatsApp or Telegram or something else, you just are in a group and you receive every message which is sent to the group. And in the end, the architecture functions with the same pattern there. How does it work together with the DIAS nodes, like the Copernicus DIAS nodes? So in the end, you can do some pre-processing steps really fast and really easily on the DIAS nodes. But you might have data which is open data or your in situ data in your agency, which is too large to be processed on the DIAS node, which is remote, because then you would have to publish your data or transfer it to their node as well. So the idea here is that you sequence each processing step due to the distributed messaging architecture and process a certain amount at the DIAS node and a certain amount in your data center. And as you decrease the volume of the data you need to process after each processing step, because you have an intermediate pre-processing result, basically, you can then transfer it to your own data center. So the message here is, if a Copernicus DIAS node tells you you need to process everything on their system and their cloud environment, that's simply not true. You can connect both infrastructures and couple them together, and the architecture pattern from the previous slide basically allows you to do that. And this is really important because often I have received comments from agencies that they have large-scale data at home in their databases and data stores, which can't be processed somewhere in the cloud, so they need to do it at home, and this is the basic requirement for combining OGC/Inspire data and Copernicus data, which is there, to have both worlds interconnected. How does it work? Where we are at in the project at the moment? We have deployed more or less everything at the moment at the Open Telecom Cloud, which is infrastructure as a service offering by IT Systems, which is coupled to a Copernicus DIAS node, which is called Mundi Web Services. And we have basically two portions in the infrastructure. We have one static side of the infrastructure, which is your standard spatial data infrastructure components, so a WMS, a WFS, a WCS, and all those things, which are static resources. They are never touched. They are always there and always accessible. And then we have the dynamic portion of the infrastructure, which can be shut down with one simple command, basically when there's nothing to do, which basically processes everything. And that works, as I've told you, with Apache Kafka and Spark, and basically the entire infrastructure is managed using Kubernetes and Docker, which are two vocabularies you might have heard before, which allow you to highly virtualize and run in parallel certain infrastructure components without needing to manually install them on each machine. So if you say we need to process something, an event is fired, the infrastructure folds up using Kubernetes and Docker, is deployed, everything is processed, then stored in a standard database in your standard spatial data infrastructure, and then the entire processing infrastructure, the dynamic side, is shut down, and we save cost and only have the cost for the standard OGC services which we need to distribute the information out there, but not everything which actually processes the data. In the end, what's up with the picture? How does it look like? How does an open water body look like at the current time in the project? I've brought you a small GIF file which shows you a river. It's Rhein in Germany, the River Rhine, and it's a scene which was calculated from a flooding event. And you can see, if you look at it for a while, that the black portions, which are the open water bodies, if you're familiar with remote sensing, you kind of know that in radar data, open water looks like black due to the reflectivity, how it grows basically with each passing time step. So this is a scene which was collected over a couple of days, and you see how the river swells and floods the adjacent space to the river. And that is the result of the automatic processing. So we have basically pushed everything to the infrastructure. We have processed a couple of known flooding events from the past and are now working to do actually the folding up of the infrastructure when a new flooding event is prognosed by the German weather forecasting agency, saying, well, there's a lot of rain coming and we know that it starts there and then it goes down the river, and that the entire infrastructure folds up and then does the processing only for the parts in space where we expect to be a flooding event. So by the end of 2018, we will have the technical prototype, a version 0, which is set up completely. And we have the demarcation of the flooding events. We have the production environment completely up and running, and the processing chain is well established and tested. And in 2019, which is the second part of the project, which is still upcoming, so we've got roughly 10 months left on the project, we will tune the classification and the technical approaches and do validation, because, well, you can always say you have detected water, but everybody from remote sensing knows it's a bit tricky, and you have to really check if what you've detected is actually water, which is upcoming work. Well, this would conclude my talk. Thank you for your attention, and if you've got questions, feel free.
Thank you, Mr. Fechner. Do you have any question?
Hi. Have you taken a look at any other infrastructure providers other than telecom?
Yeah, actually we have had a pre-project running on Amazon Web Services, which is actually a bit nicer because of the tooling which is available there. But we have basically set the entire thing up on Amazon Web Services and now on Open Telecom Cloud. But in the end, it's interchangeable where you host it. So an Azure Cloud would also work as well.
Okay. Hello to everybody. I am Francesco Facchinelli. I am a student of the Padova University, and I am a collaborator with the Master in G-Science and Unmanned Aerial Vehicles. I'm there to present you my bachelor thesis on using NOAA night fire data to map and monitor gas flaring in high biological and cultural diversity areas, the case of Yasuni in the Western Amazon. Okay. The Yasuni Biosphere Reserve is one of the most biodiverse areas in the world, as you can see, in the Amazon rainforest, sorry, and maybe in the world. It is also the ancestral home of the indigenous population Waorani, of which 2 tribes are still uncontacted. Gas flaring consists on the burning on-site of the dissolved gas, mostly methane, in the raw oil. This is not only a waste of energy, but is also a process which has huge impacts both on a global and a local scale. In order to map gas flaring, we used data from the National Oceanic and Atmospheric Administration, elaborated through the algorithm Nightfire, and on imagery from the Suomi NPP satellite, which has the particularity of a repassing time of 12 hours. So it provides one image in the day and one in the night. But the very useful thing which makes this satellite very well fitted in order to monitor gas flaring is that during the night it maintains active its ER channels. So it is possible to make a multispectral analysis based on the Planck curve, okay? And then determine the temperature of the object that we are studying. In this case, the gas flaring has a temperature of 1,800 Kelvin. And as you can see, is the band M10, is really well fitted. In fact, despite the relatively low resolution, which is of 750 meters, which is a dimension a lot bigger than the flare, it allows us to identify them and to discriminate them from the electrical lights, for example, or from biomass fires, and of course from the background. So we use the dataset provided from NOAA in order to make a spatial and a temporal analysis. The databases were georeferenced and were from 2012 to 2016. We made spatial and temporal analysis, but also we used estimated volumes of flared gas in order to identify more exposed sites. As you can see there are the bigger flares and the smaller ones, basing on the dimension of the circle. And this evidenced the presence of increasing trend, both on a regional scale, we are in the Amazon region of Ecuador, but also in the Yasuni Biosphere Reserve. It also highlights that a quarter of the flares in the region are in the Yasuni Biosphere Reserve. So, as a second step of the process, we used an intermediate product, which are daily detection, in order to make a near real-time monitoring and to look for additional flares. So, we made a merge of daily files from the 1st of January 2070 to the 3 of March 2080. We compared them with the annual databases that I mentioned before, and for the detection which could not be attributed to flares of the previous years, we used the clusters of more than 3 detection in a 1,200 meters radius, and we calculated the centroid. This allowed us to find 2 particularly interesting flaring sites. The first is the case of the Tiputini oil field, which where the extractive activity has been highly discussed due to the position of this oil field in a particularly high biodiverse area in the Yasuni, and also for its proximity to uncontacted indigenous territories. So the extraction in this site must, yet for political declaration, this is the vice president of Ecuador at time, which present at the beginning of work in the Tiputini oil field. But also in the environmental impact assessment is said that gas flaring could not be employed in the platform. Anyway, we found 10 detection. Exactly there you can see the oil field, and there are our detection. The second case is the case of the Armadillo oil field. Also, there, the extractive activity is highly discussed due to the probably presence of indigenous population in voluntary isolation near the oil field. It is important to note that the Constitution of Ecuador allows to the indigenous the right to the possession of their ancestral territories. And we found 6 detection in a period of 4 months. So the further development of our analysis have been the confirmation of some data. We made it through ground truth, which have been carried on from the research group Territories of the Ecological and Cultural Diversity of the University of Padua, through taking geophotos fundamentally, and through visual analysis in Google Earth Pro, as you can see. This allowed us to confirm a total of 50 flares and to find 8 new gas flaring sites. One of them is the Armadillo oil field. Okay, is in the Armadillo oil field. Finally, we used bibliographic metrics in order to try to estimate radius of impact and then areas of impact, but on the ecosystems, we used a 2-kilometer radius, and we found that a potentially impacted area of 300 kilometers in the Yasuni biosphere reserve that you can see there, and 8 different tropical ecosystems for more than 450 square kilometers. Okay. We made the same for local communities. We used a 5-kilometer radius, and we found 120 schools, 178 populated centers, 158 indigenous communities. So, the main things that we have understand in our study is, on the first hand, the increasing trend in the Yasuni Biosphere Reserve, which is actually weakening the UNESCO protection framework. Also because the UNESCO zonification allows just ecologically compatible activities in the area of the reserve. So it is not only an environmental problem, but also a problem of application of directives and this. Also, the presence of undetected flare from the algorithm tells us that it is even important, the ground truth, and that there are the development possibilities for the algorithm, but also that probably the extension of the phenomenon in the region is bigger than what we saw in the present study. The absence, making the bibliographical analysis, we found a lack of knowledge on the impacts of gas flaring in this kind of context. It is important to say that respect to other study complex contexts, there the impact may be more elevated due to the high vulnerability of tropical ecosystems to dryness. There are a lot of studies about this, but also of the indigenous communities which, due to their lifestyle, are more exposed to the contamination of their environment. Lastly, it tells us that there is a high potential of employment of this kind of data to monitor the gas flaring activities, but that is also crucial to embed them in GIS analysis in order to not only get the data, but also to understand what there is around the data and the processes which are happening beyond. I just wanted to mention that during the time that we were doing this study, some local movements began to ask for the end of this kind of process due to the health damages that they have found during 20 years of gas flaring activity in the region, and I just wanted to mention this because it reminds me why we are making this kind of analysis, that in the end it's for the people. And I finished. If you want further information, I am there. And anyway, in the presentation, I put my contact email, the research group website, and some useful articles. Thank you.
What are the environmentally responsible ways to deal with the methane gas that's produced as a byproduct, other than flaring it?
The byproduct of the gas burning? Mm-hmm. Yes. Allora, firstly, the methane, okay, is not completely combusted, burned. So part becomes methane and another part becomes CO2. On the other end, we have anhydrides of sulfur, of nitrogen, and sulfuric acid, which goes in the air, okay, and produce acid rains. And we have thermal impact, for example, which has both an impact on the ecosystems, but also on the people. Another effect on the people is the presence of continuous light, because for somebody which lives near the plants, have been studied that it has hormonal effects. And also, of course, there is the production of particulate matter, okay, which affect the air system, the respiratory system of the people. And what else? Organical component, volatile component. There are hydrocarbons with a short chain, okay, which can have different effects. I think I hope to have remembered all the components.